Welcome everybody. I'm very happy to be here to present the first CBB seminar of the fall 2017-2018 series, and I'm even more happy to have as first speaker Jared Maxson from Classe and Physics Department at Cornell University. Who has recently joined Cornell University after obtaining his PhD here and working as a postdoc at UCLA with Professor Musumeci. So we are very happy to have him back and to have this interesting talk about extreme regimes of beam production and transport in bright electron linacs. Okay, so now I will give the room to our speaker, and I hope everybody will find this interesting. Thank you.
Okay, can I be heard for those remote participants out there? Can we get any confirmation that I can be heard from the remote participants?
Yeah, everything is fine. I can hear you.
They can hear me. Excellent. Very good. Okay. So if there are questions, I'm going to try to keep an ear out for the remote participants who will be piping up over here. So if I stop abruptly, that may be because I'm walking over there to try to listen into what they say. And I will repeat it for the rest of us. Okay. What has happened?
Oh, that's right.
I would try that X there, yeah.
Yeah, try. A reminder.
1 hour, that sounds good. That's enough to make sure that I won't talk too long. Okay. Okay, my slide advancer is not yet working, so I'm going to try.
Oh, you can use the arrows if you like.
I thought I could.
It was working before.
It was working before, that's correct. Okay.
Is it on?
Is what on? The presenter is on and the laptop is clearly on and it is not responding to.
Window focus issue.
Yeah, that's a good idea.
Yeah.
Okay. That might be good. All right, great, excellent. Finally, back to it. Okay, so that was the title of my talk, but I'm going to give you my secret motivation for the talk right now. So the target audience for this talk is going to be physicists, but my goal would be to try not to bore the physicists. I'm trying to find if I can move this maybe over here. I'm going to try not to bore the physicists. Minimize. I like that suggestion.
Can you hear me?
Yeah, good. Okay, so I'm going to try not to bore the physicists in the room. But here's my overarching theme that I would like to convey to you. So CBB has these 3 themes, but I want to talk about how new beam physics in bright electron linacs is likely to inextricably couple the themes of beam production and the themes of beam transport. So as an introduction, I want to motivate why we're interested in bright electron linacs, particularly photo emission based linacs. So I'm going to give an overview of what they're useful for as probes of the small and take as case studies ultrafast electron diffraction and X-ray free electron lasers. After that, I'll talk about the first coupling of the two themes in of CBB. First coupling is low MTE is going to require new beam dynamics. I'll define all of that. Next coupling, cold beams and intense lasers make new photoemission phenomena. Coupling 3, small sources and new simulation paradigms are necessary.
Sorry, okay. I can only see the first
and like any CBB event, all questions at any time are more than welcome. So, and that goes for you too, remote participants. Please
sorry.
If there's any technological or otherwise. That's okay. It's okay. Well, we're getting it. There we go. Okay. So CBB and its themes, there's themes of beam production. The beam starts somewhere. Beam acceleration. The beam gets accelerated. Here we focus on SRF cavities. And beam storage and transport, where we try to take the high brightness electrons that we created in the beam production category and transport them to their ultimate goal or store them for their ultimate goal. I'm going to make an argument that bright linacs stimulate a lot of crossover, this region of interest right in here, between these two phenomena. So electrons generate useful probes. A blanket statement, let me try to explain it. Electrons are charged particles that are plentiful, and as beams go, they're relatively easy to produce because there are many emission modes from solids. You can get them by thermionic emission, by heating up a cathode. You can get them by field emission, strong fields on a cathode, and you can get them by photo emission, which is going to be the focus of this talk, where you use a laser to liberate electrons from a material. Electrons themselves are also very light. They're about the 1,000th of the mass of a proton, give or take a few factors of 2, which makes them an extremely efficient medium for converting kinetic energy and high energy accelerators into high energy focused electromagnetic radiation. We typically do this via bending magnets. Bending magnets range from simple, such as a single bend, to more complicated, multiple bends like a wiggler. And if you play the electromagnetic game correctly, you can get coherence effects, and coherence effects happen in a subset of wigglers called undulators. And one interesting example that I'll focus a little bit more on is if you drive a beam into an undulator with extremely high density of electrons, one interesting thing that happens is the free electron laser process. I won't go into the physics of the FEL process too much, but suffice it to say that a huge number of X-ray photons can be generated. Typically on the order of 10 to the 9 more coherent photons can be generated here than can be generated in third generation light sources. So it's an extremely powerful and revolutionary tool for X-ray physics. What kind of X-ray physics is done? Well, first of all, where is it done? A good example of an X-ray free electron laser was the first hard X-ray FEL in existence was a linac coherent light source at SLAC, and they lasered soft and hard X-rays using multiple GeV electron beams, multiple kilometer scale linac for this kind of machine. So kind of interesting science that they do is it's very hard to tell you about all of it. I just chose what I thought was a very interesting example. It's a thing called coherent diffracted imaging. In this case, you take a very intense laser beam, the X-ray laser beam, and you have it pass through a very small sample with some structure inside, and somewhere between microscopy and diffraction, the fringes that are formed on the X-ray detector can be inferred back to the sample to tell you what the microscopic structure is. And you need a lot of electrons, and they need to be very coherent. In this case, they were looking at individual atom clusters of xenon inside of a superfluid helium drop, which is just a bunch of cool words suddenly together. And they do this kind of high-level physics every day at the LCLS. So electrons generate useful probes, but they are useful probes. Electrons, even at low energy, like 100 kilovolts, have single picometer scale wavelengths, much smaller than light, much smaller than even hard X-rays. So this makes them a useful probe of lattice structures via diffraction and imaging. And this is the entire field of electron microscopy. And one of the most exciting examples I can think of things going on in electron microscopy now is the advent of using biological samples. You can do direct imaging, which is being done in UC Berkeley, notably by Eva Nogales, where they're looking at direct electron imaging of cytoskeleton building blocks, molecules themselves. And in the Gonin lab at HHMI Janiela Farms, they're doing a thing called microdiffraction, where they take micron scale crystals and using a complex reconstruction process, they can take diffraction patterns in many orientations and do a reconstruction of large scale macromolecules. So electrons generate probes, and electrons are very useful probes. So in particular, linac electron bunches can be extremely short, allowing us to get time resolution in the scattering processes which I just described. And the direct corollary of this is ultrafast electron scattering, such as ultrafast electron diffraction or microscopy, which is essentially taking electron microscopy or diffraction and adding extreme time resolution. And the way this works is as follows. You use a very short laser pulse to create a beam via photo emission, and you compress it further, if you like, using time-varying electric fields. So in the picture down below, we create an electron pulse with a short laser, we propagate it towards a sample, and then we stimulate the sample with a synchronized pump. to elicit some time-dependent change within the material. That can be lattice vibrations, that can be heat deposited into the material. Typically, as pumps, we use lasers or other things that are easily synchronized with photoelectrons, such as terahertz radiation generated from lasers. And the final story is that ultrafast electron diffraction allows you to make essentially diffraction movies in time by varying the delay between the pump and the probe. It's a very powerful and very exciting, relatively new field of ultrafast physics. So how fast is very fast? I've just said words like extreme and fast. So let's put actual parameters to those words. So electrons probe lattice details. The cross-section of scattering with a lattice is very high as opposed to scattering with the electrons. So we want to think about what the fastest lattice motions are. Well, it turns out that the fastest phonons, the phonons with the smallest period, have periods in the tens to hundreds of femtoseconds. That's really fast, and a modern day, a sort of at-home example of this would be light will move the width of a thin human hair in about 100 femtoseconds. So it's an extremely short, a short time. So as an example of how short you could make pulses like this, I cite a recent paper that we produced when I was a postdoc with Pietro Musumeci, using a relativistic photogun and time-varying electric fields. We created a beam, we accelerated the beam, we compressed the beam, and thanks to the very nice compressibility of electrons, the bunch length is extremely short. Here we measured a bunch length with RMS duration of about 7 femtoseconds, which should hopefully be good enough to resolve even the fastest lattice motions. So this is where we're headed in terms of ultrafast electron diffraction accelerator physics. So how fast is very fast for an X-ray free electron laser? Well, how compression works in an XFEL is actually by using magnetic fields to delay certain particles relative to others, essentially making electrons that are at the head of the bunch take a longer time to get across a section of a magnetic band than electrons at the tail of the bunch, thereby compressing them. So for GeV electrons at SLAC, they're able to get down to about 3 femtoseconds, which is extremely short. It's one of the shortest electron beams that I personally have ever seen measured. And one of the interesting examples that they're doing with this time resolve capability is looking at interesting electronic properties in time. For example, here's a picture, an artist's conception of what a magnetic skyrmion might look like in lattice form. A magnetic skyrmion is essentially just a spin lattice, and if you form it's a spin vortex, and if you form a lattice of them, you can see images, you can see the signature of the skyrmion in X-ray diffraction. So using X-ray diffraction and using a pump, they're able to resolve the stability of the fermion with respect to different pumps at extremely small timescales, talking about single picosecond resolutions and smaller. So I hope this is enough to convince you that there are people who are taking the electron beams that accelerator physicists produce and doing really interesting science with it. And just a very short introduction to that. Okay, so brightness is a thing that characterizes a beam phase space density. It's what we're after in the Center for Bright Beams. And the reason I've talked about UEDs and XFELs is brightness is the key to their success. Brightness in general is a 6-dimensional object. We think about the density in 6-dimensional phase space of a number of electrons, where n can vary from 1 all the way up to 10 to the 10 in the XFEL case. And the position space and momentum space are lumped together. I unfortunately can't draw it in 6 dimensions for you. I want to make a note here that throughout the talk I'm going to be using the z-axis as the direction of motion for the beam, and the x and y directions are the transverse directions. So the brightness is something like the density in the 6-dimensional phase space, but in practice, our diagnostics often measure one of those planes, not all 3 of the planes at the same time. So we project into the x, px, y, py, and z-pz planes. The x, px, and y, py, z-pz planes, they do different jobs. Typically, the x, px, y, py plane have something to say about the spatial resolution of the scattering that you're doing, and the z-pz has something to say about the temporal resolution, but they are actually coupled in a number of interesting ways. Which we'll get to in just a second. So we ascribe in this phase space, we ascribe an area in the RMS sense, and we call that area the emittance after we've removed any linear correlation. And hopefully this should all be a review for many of the people who have been in CDB, but we form the brightness simply as the ratio of the number of particles divided by the phase space area, or if you're not interested in momentum spread, you could say the 5-dimensional brightness, the current divided by the 2 emittances. So I brought up the planes doing different jobs. In ultrafast electron diffraction, the coherence length is essentially proportional to the square root of the brightness, thanks to the dependence on the transverse space. But the FEL, considering that it's a function of both the instantaneous density inside the undulator as well as how small the beam is transversely, that's actually proportional to the brightness to the 1/3 and takes all 3 of the phase spaces to make a good FEL. Okay. So, linacs sources for time-resolved science. We do fast photo emission, and with 3-dimensional pulse control on a laser. That's what really makes photo emission such a powerful tool, is that we can control the shape and the time over which we're emitting electrons. Linacs are, in this sense, are single-pass machines. The beam never reaches equilibrium. The beam is generated by a laser, is accelerated. The electrons are then accelerated. They may be boosted. They may not be boosted to higher energy, they're used and they are dumped. And nowhere during the process does the beam reach any kind of equilibrium. So when we generate the electron beam, we generate a phase space picture. And I'd like to instill in your brains that we always think in phase space pictures when we're thinking about linac brightness. So I generate some number of electrons, and that number could be 10 to the 6 electrons if I'm trying to do ultrafast electron diffraction. That number could be 10 to the 10 electrons if I'm trying to generate high energy X-ray pulses. That the initial distribution has some characteristic size, the size being set by the laser size. And the distribution also has a characteristic momentum size. The momentum size is a function of the photocathode emission process. We'll talk a lot about that later. So these are interacting charges when they are created. The 6n-dimensional phase space from statistical mechanics, that is an object that has its density conserved. But it's 6n-dimensional and is thus pretty intractable to use or measure. We have a nice simplification that occurs typically. However, typically, sigma px is large enough that individual electron interactions are screened. They're blurred out by the relative motion of their near neighbors. So, often, if the sigma px is large enough, the electrons interact via the mean field. The mean field force in our brand of physics is called space charge. If we say that the particles are only acting via the mean field, the Hamiltonian that describes each and every individual particle, that describes the whole system, can be separated into ones that describe each individual particle, and they are not interacting only via the mean field. This means that the 6-dimensional phase space density, this xpx, ypy, zpz, that phase space density is actually preserved. So I get rid of the particle picture and I move into a continuum picture. I have a continuum density in momentum and position space. And I ascribe to that some area just as we did before. Okay, so the question I want to ask is linac brightness just set by the source? And the answer is not so fast. Transport is intimately involved in the formation of linac brightness. Starting with an initial phase space, if all the forces on the system or all the momentum shifts in the system were linear in the position of the particles, then indeed the emittance would be conserved. The RMS emittance would be unchanged. However, arbitrary transport means that you'll go through fields which have not necessarily linear dependence on the transverse coordinate. And so you can get folding in the phase space. You can get growth of the tails of the phase space, and the final emittance may necessarily be larger than the initial emittance, and that's definitely something we don't like. But Liouville's theorem still applies. The peak phase space density in the center of the system is still a constant. So How do these twists in the phase space arise? They arise from nonlinear forces, and one of the forces we have to think about very carefully if we're trying to if we're using a high brightness linac is the force of space charge. The force of space charge is the mean field Coulomb repulsive force, and you can think about it in a certain sense like a generalized aberration. So if I have some distribution of particles that's not necessarily uniform, say it's Gaussian, and I calculate the force over the position inside of this bunch due to the bunch itself, I find that indeed in the center it's nice and linear. That's like a defocusing lens. However, near the edges, the lens behavior turns nonlinear. That's essentially like a nasty spherical aberration in this distributed, generalized electron lens. There's another thing that we have to worry about. Since electron bunches have a physical extent in longitudinal space, the head of the bunch, the middle of the bunch, and the tail of the bunch may be doing very different things. Thus, in linacs, we have to worry about the fact that slice 1 and slice 2 may have different focusing forces on them from space charge itself. And so this is like a generalized chromatic aberration where the head and the tail may have different energies. The head and the tail may also have different space charge repulsive forces. We typically calculate these effects with very detailed space charge simulations, and we control them in experiment with laser pulse shaping. Now, let's get into some of the more exciting stuff that's happening in CVB. Now, Theme 1 of CVB has a goal to make the initial momentum spread of photo emission as small as possible. The parameter that we talk about in Theme 1 is sigma px sometimes, but more often than not, we talk about the mean transverse energy, which is essentially analogous to the effective electron temperature, the RMS, the square of the RMS momentum spread of the electrons as they're being emitted. So I'll interchangeably use these two. Sigma px is directly proportional to the emittance. So in Theme 1, we have long been searching for the ability to use the rich band structure of materials, the rich momentum structure inside of materials, to create beams that have very little momentum spread. But we haven't had a lot of luck until recently. So a very exciting paper from Siddharth and collaborators at Berkeley has shown that there is new evidence that we are actually starting to see some of this rich momentum structure coming from photo emission from ordered surfaces where you really pay attention to what's going on in terms of contaminants on the surface. And so instead of a Maxwellian velocity distribution, Siddharth has measured large deviations from Maxwellian charge velocity distributions, things that are peaked in the center, things that have dips in the center. And what I want to point out to you is that might not be alarming to you at first blush, but if you consider the path of an electron and an accelerator, which is focused and defocused, focused and defocused, the position distribution soon becomes the momentum distribution. And the momentum distribution soon becomes the position distribution. These new momentum distributions are going to have to change the way we think about the physics of space charge simulations. We're going to have to take these non-standard momentum distributions into account, and particularly right where we care about them, right where the beam is densest, the spatial distribution is dominated by the momentum distribution. So in terms of electron optics, this changes the way the beam goes through a crossover, which is some of the most critical points in the beam's lifetime. So I've shown you one way in which beam production is changing the way we think about beam transport. Here's a more fundamental way where beam production may change the way we think about beam transport. If you supply me with a photocathode that has an MTE much, much smaller than the average near-neighbor potentials of the Coulomb near-neighbor interaction potentials, that Hamiltonian that I said was just fine to approximate as in the mean field is no longer a good approximation. So the 6-dimensional phase space density is no longer conserved. This is very interesting because one of the effects that we predict from this is a new effect, which has been called disorder-induced heating, which will happen right next to the photocathode. So, say we generate a distribution in space of electrons that has no initial momentum. momentum will be generated, and effective MTE will be generated by the fact that the microscopic positions of the particles are randomized when they're emitted. The random interaction potential energy will be thermalized. We'll move that randomness from the position space into the momentum space. So we'll get a more ordered position space at the cost of emittance growth, at the cost of growth of MTE. So this is a new effect. This is, in one sense, it's not so great. This is heating. So we're taking the initial potential energy, we're turning it into heat in the beam. This has actually already been observed in laser-cooled plasmas, and we've done some simulations to show that it can be about the 5 millielectron volt scale in photocathode materials. And it may be a strong photoemission brightness limit. We're not quite at 5 millielectron volts MTEs yet, but we're on our way. But it's also exciting for me because it fundamentally changes the way we think about beam transport. No longer is the six-dimensional brightness an invariant in the accelerator. Binary interactions dominate, and you have to think very carefully about how you calculate the beam, the beam's self-interaction as it propagates down the beamline. Very interesting physics. Right. So those are two ways in which, well, let me give you the recap here, and I'll say what I was just going to say. So photoemission linacs create electron bunches which are dense in 3D, and I've hoped to show you that they are useful. It's perhaps not so surprising to think that brighter photocathodes will change the way that we think about beam transport. If the beam is coming off differently from the photocathode, we have to treat it differently. Now, how about the other way around? In what ways will beam transport change the way we think about photocathode physics? And I want to go through a couple examples of that. The first example I have of that is cryogenic photoemission when we're emitting near the photoemission threshold. But before I go on, I realize I'm blazing through this talk and I haven't heard any questions. I want to make sure that no one's feeling hopelessly lost or confused or totally bored. Maybe the third, but okay, Richard.
Will you go back 3 slides?
Two.
Okay, that one.
That one.
What are the purple curves and the two white curves in that graph?
The purple curve. And the purple curve is a measured momentum distribution. The red curve here is an excellent question, by the way. The red curve is a predicted momentum distribution from the band structure. And so what, if given time, and if asked this question, what I would have said to you would be that we are on our way to understanding how the photo-emitted electron momentum arises from the band structure, but we're not there yet.
So on the left is theory, and on the right is observation.
Blue is observation, red is theory, in 2 different wavelengths in this particular sample, if I'm correct. Make sense? Good question.
That's impressive.
What's that?
That result.
Oh, it's just a lovely result. Yes. So all the credit goes to, this is not my result at all. This is Siddharth Kakkare's result at Berkeley.
So one of the promising materials?
As far as I understand it, I'm not a material scientist, but it was silver 111 is a surface that is a benchmark surface to prepare. You prepare it when you want to know that you've got a clean surface, and it has relatively straightforward recipe to make it.
If they can make similar performance in one of these things with the right band structure.
Right. Exactly.
But of course, it may be more sensitive once it gets really down.
Yes, right.
Sure.
Yes.
So on this slide.
On this slide, yeah.
You have the disordered, the unorganized electrons right after they're generated.
Yes.
And then they repel each other.
Yes.
And you get a more ordered structure plus some temperature.
Yes.
Could you just explain how this picture would change if they were initially created in some ordered state?
Very good. There's actually been a number of papers written about this. So the question was, repeating it for the people at home, I realize I didn't do that before, my apologies. The question was, what if we generated electrons instead of in a disordered state, but we somehow nanoscopically structured our photocathode to generate electrons on a lattice, for example? And indeed, that is where you would get rid of disorder-induced heating. If you were able to generate electrons that were in an ordered pattern, you can calculate what the correlated potential energy is, and it's much, much smaller. And it's a way to circumvent almost entirely most of this effect. However, it's a pretty hard thing to do, considering that our beam densities have typical electron-electron distances of about a nanometer in the most extreme cases. So it's hard to do, but that has already been written about. For example, people have been looking at that effect in ultra-cold neutral plasmas, where they actually think they might be able to do it. More on that if you're interested, and we could perhaps talk after. Okay, so cryogenic photocathodes, photoemission at threshold. So first I want to answer what the role of photocathode temperature is on the mean transverse energy of photoelectrons. So let's start with a free electron picture of a metal. If I have some solid, and in this picture, the solid essentially exists as a potential well into which I can pour electrons. I pour electrons up till some energy. That energy is called the Fermi energy. And there is some potential energy there's some energy difference that I need to give them in order for them to escape. That energy difference is the work function, phi. And the temperature of the system ends up adding a little blurring to this energy distribution right near the top of the energy scale, right near the Fermi energy. Okay, so how do we generate photoelectrons? What we do is we send in some laser light. Photon energy h nu. H is Planck's constant. Nu is the frequency. There's a finite penetration depth that goes into the sample a finite distance. There's also a finite reflectivity. We bounce some electrons back off. So once the light gets into the material, we pick up some portion of the electrons that are within h nu of the Fermi energy, and we promote them up h nu. And if they have sufficient enough energy, they can escape. Sometimes they fall back down because they bump into each other, and sometimes they get reflected. But from this picture already, if we assume that the electron's momentum is pointed in an arbitrary direction, we can derive what the photoemission MTE is. If the photon energy is much, much larger than the work function, the MTE is essentially the difference between the photon energy and the work function. And since there are 3 dimensions in space that this thing is distributed into, we get a factor of 1/3. However, if we go near threshold, where we go equal to or less than the work function, the MTE should, in this picture, be simply the material temperature, because the only residual momentum spread will be due to the blurring at the Fermi energy. Does that make sense? Okay, so can you measure it? Does that actually work? And the answer is yes. In some cases, near threshold, MTE does very much tend towards KT. So this is an example, again, by the Berkeley group, where they've taken oxidized antimony, and they've changed the excess energy. Excess energy here is just the difference between the photon energy and the work function. They've slid the excess energy down to very near threshold, and their emittance plateaus exactly where you would expect. If I change this into MTE units, that would be 26 millielectron volts, or the energy of KT at room temperature. So this is an obvious way to decrease the MTE. You can cryo-cool your photocathode. So that's exactly what we've done at Cornell. Luca Coltrera and Professor Ivan Bazarov have been heading this work up, where they take a different kind of cathode, alkali antimonides, and they have some MTE when they're warm, not quite KT, but close, and they reduce their temperature down to liquid nitrogen temperatures, and they get a much, much smaller MTE. So this seems to be a strategy that works out. In the alkali antimonide case, we don't quite get the KTs that we'd expect, but the emittance does indeed improve. So note, this only works for materials that are well modeled by free electrons. So all that rich band structure stuff, this argument does not apply. So, cold photocathodes at threshold. What we're doing here is essentially we're doing an energy filtering. We're saying I only want those electrons that are really close to the Fermi energy, and I only want and none of the others. So, an example of where you can compute this is in polycrystalline copper. You can see that as you reduce the work function, as you reduce the photon energy, the MTE will plateau. If you cool it, the formulas show exactly what you had anticipated. But one thing that you can also calculate is the quantum efficiency. In copper, the quantum efficiency was never terribly great to begin with. You needed 10 to the 5 photons at high quantum efficiency to liberate a single electron. However, as you keep going down, the quantum efficiency drops and drops and drops. And as it goes down even further near the Fermi tail, the Fermi tail itself is very dependent on the electron temperature, and thus the quantum efficiency is 2. So The low QE gets lower and still lower when cold. So even notable high QE semiconductors suffer from this, alkali antimonides, which when you have high enough photon energy can have percent QEs, so only 100 photons per each electron that you get out. So that's quite nice, except going towards threshold, they get down to the properties of essentially what a bare metal would do. And they get even worse when you cool them down. Going from 300 Kelvin to 90 Kelvin, the QE drops by essentially an order of magnitude. So what is this doing? It's a route to low emittance, but under what conditions? Because if we are to use this for any application, it's going to drive the required laser fluence way up. And the question I want to ask is, at what point does the unproductive absorbed laser energy change the electronic distribution and hence change the MTE? Okay, so let's do some back of the envelope calculations. So how much fluence is actually a question of how much charge density you need for your particular application. So this is an application and transport question. So if you have some electric field that you apply to your photocathode and you give some photon energy to the sample, you'll emit a charge density sigma. The charge density sigma, as it accelerates forward, will have a space charge force that's pushing back against any electrons that are being emitted. There's also an image charge density, which essentially doubles the effect. Now, the application, the transport information here is that when the repulsive force of the charge density exceeds the accelerating force, emission stops. That's the maximum amount of charge density you can get out of your material. So if the particular application will decide how close you want to get to this hairy edge. So all I'm saying is that the transport properties, as in theme 3, beam storage and transport, of the accelerating field and the space charge dynamics set the required laser fluence. So let's run some numbers. So if we assume if we're emitting near photo emission threshold, we have a 10 to the minus 5 QE, and we have an accelerating field typical of, if I did an average of all manner of electron guns of 30 megavolts per meter, and I used a visible photon, say at 2 eV, I get 5 millijoules per centimeter squared. I'm sure to many of you that's not a terrifying number, it's just a number. But if you look up what 5 millijoule per centimeter squared is, this is pretty darn close to where metals start to burn up. You start to ablate them. In copper, another way of saying this is in copper, all the unproductive absorption, you can calculate excites 1% of all of the density of the conduction electrons in copper. Since we are interested only in the fraction of electrons that exist at the Fermi tail, this 1% of all the conduction electrons is probably a huge effect. So this was just a warning slide, warning that here the effects of laser heating may be very significant. And it turns out you can calculate this stuff, and this is what I've been working on in collaboration with a number of other CBB groups. So to first order, you can model the unproductive excitations as becoming thermalized into heat in the electronic distribution. So we model this with the famous 2-temperature model, wherein the electrons and the lattice are treated as isolated, they're treated as interacting thermalized subsystems. They're not quite isolated, and they interact via a specific way. So we can write down a differential equation that governs the electron's temperature, which of course depends on how much laser energy you're putting in. It depends on the electron thermal conduction, and it depends on how often the electrons collide with a phonon, giving heat from the electronic distribution to the phonon distribution. And so you can do the same for the phonon distribution. The phonons don't absorb photons. They do scatter with electrons, and here we're ignoring their thermal conduction. The source term is just whatever laser shape you have, and it has some penetration depth into the sample. It's actually a very simple set of differential equations to solve, but it's actually extremely successful when you study what happens to the electronic temperature via time-resolved reflectivity. So these are famous measurements done looking at the reflectivity when you first heat the sample with a laser pulse and then test its reflectivity with a probe laser pulse. At different versions of pump probe delay, you see the reflectivity change, and you can see that the time scale for these changes is few picoseconds. It turns out if you do the calculations, it takes several picoseconds for the lattice to effectively cool the electrons. The electrons remain hot for perhaps almost the entire duration of the laser pulse. So if we use a free electron model of the QE and MTE as we've been doing in copper, it's a good example, what you can do is you can calculate for a pretty intense laser pulse. This one is on the order of 5 millijoule per centimeter squared. You can see that the electron temperature, here shown in black, rises to about 3,000 Kelvin. What you were hoping was a 300 Kelvin electron system is now 10 times higher. The lattice only kicks in after multiple picoseconds and scatters some of the thermal energy away. Why the lattice doesn't get so much hotter is that the lattice heat capacity is so much larger than the electronic heat capacity, which is part of the problem. So if then we take this temperature and we compute what the emittances would be from as we go along. Here in the dotted line is the outline of the laser pulse. If you have a very high excess energy, the emittance doesn't really change all that much. Most of the electrons that are coming out, are their RMS momentum spread is determined by the fact that they have a lot of excess energy. The temperature changing a lot doesn't really matter. However, if you decrease the excess energy towards zero, in the beginning you have 300 Kelvin type emittances, and it changes all the way up, changing by, here a factor of more than 3, up to 3,000 Kelvin emittances. So what's important to note as the emittance that you would calculate for this pulse is large, almost the entire duration of the pulse. Only after the pulse does it come back down. So what you can also show that the quantum efficiency is similarly affected. The quantum efficiency here, I'm normalizing to some quantum efficiency scale. The quantum efficiency is relatively unaffected when there's a large number, when the excess energy is very high. However, again, it's wildly affected, 2 orders of magnitude in this case, when the excess energy is very low. So this is a good way to get a number of electrons out if the excess energy is very low. However, you were hoping for good emittance and you didn't get it. So, and this is a very interesting thing. Due to the laser fluence required by the application, the MTE and QE are no longer static properties of the material, they're dynamic properties of the material. So one thing I want to get to, I want to just briefly mention is that if an application specifies a required charge density, oh yes, there's a question, go ahead.
Should I be thinking of the electrons in the whole photocathode getting hot, or just within some? Within
the skin depth. So the question was, should you be thinking of the electrons in the whole cathode getting hot, or are they in some finite region? And yes, indeed, they're within a few skin depths. Go ahead.
How much does the electron-photon coupling change between different photocathode materials?
That's an excellent question, and what I think is a really interesting route of research. We simply don't know for a number of the photocathodes that we use. For instance, the alkali antimonides, the electron-photon coupling, to my knowledge, has not been measured. So one of the things that we could do is to perform measurements of this type to actually give solid state physicists some information from our accelerator measurements.
Or ask Thomas or
Yes, of course, absolutely. Yes, that's right. That's right. Any other questions? Georg.
So you showed that for copper, which is kind of the worst case, I guess.
Yes.
You're telling
However, it's a very common case. The current LCLS photo gun uses a copper photocathode.
So are you going to tell us something for other cathodes?
No, because I simply don't know how to calculate them yet. The free electron picture is a very simple picture in which to model stuff, and we can get tractable results. We're currently working on extending this to semiconductor cathodes. So it is definitely in progress. I'm not ready to show it yet. That's an excellent question. Any other questions? Okay, so what I wanted to show you is an interesting thing pops out. If you say I need a certain charge density out of my material, you can then determine that there is an optimum photoemission wavelength to reduce the emittance. You can self-consistently solve for the fluence you need to give you a given charge density, where of course as you change the fluence, you change the effective quantum efficiency. But if you do this calculation, you find out that if you scan the MTE as a function of the excess energy, all the time constraining yourself to have the same number of electrons leaving the crystal, that there is a minimum. For large excess energies, the emittance is dominated by excess energy. For small excess energies, the quantum efficiency is small. The final emittance is dominated by laser heating, and there's some happy region in the middle. We've broken the monotonic behavior between MTE and QE. I find that very interesting. So this is one excellent thing to try to measure in a real photogun. Okay, so I want to briefly say that how we're trying to go beyond the two temperature model. So Georg asked about new materials. What I asked before new materials is how can I do a better job of calculating this? The two temperature model is limited. It assumes a thermalized electronic distribution. So in reality, the occupation function, the number of electrons at a given energy at a given time, is changing, and it's not changing from one Fermi-Dirac distribution to another. It's changing in a more complicated way. And one way of calculating it is via the Boltzmann equation. And the Boltzmann equation is essentially a rate equation for the distribution of electrons and the distribution of photons. Initially, this is a Fermi-Dirac or Bose-Einstein distribution. And you can calculate the quantum mechanical matrix elements for photon absorption, for electron-electron scattering, electron-photon scattering through a number of assumptions, relying on a lot of work that was done by Mueller and Rethfeld, this very popular model to do these kinds of calculations. You can actually calculate the Fermi-Dirac distribution as a function of time, not just saying here's temperature as a function of time, but the entire distribution. So explicitly looking for distributions that aren't Fermi-Dirac. The two temperature model does simplistic assumption. What we want to see how, if we take these electrons, we excite them, we take more electrons, we excite them, how does this distribution end up looking in time? It certainly will be somehow lumpy. So what we can do is we can actually do this. I'm watching the you can plot f of e as a function of time over 100 femtoseconds for a 100 femtosecond laser pulse in copper. And what you find is that if the initial Fermi-Dirac distribution looks like this, indeed, as you continue to pump unproductive absorption into the system, there is the system gets hotter, but hotter in a weird way, not quite thermal equilibrium hot. And as you keep watching, indeed, the electron-electron scattering restores the Fermi-Dirac distribution, but that's after the laser pulse essentially is over. So what you can do is you can calculate the resultant pulse structure of your electrons in time, and you can actually calculate the absolute quantum efficiency. Let me show you what that looks like. For low fluence, this is what the pulse looks like in time. It takes a little bit of time for the electrons to pop out, and once they pop out, once that time reaches this is a short laser pulse. It's a 50 femtosecond laser pulse. The emission stops, and there's some time for the emission to shut off, but that's essentially what we would have expected from our material. However, if we turn the fluence up, the shape of the pulse becomes very different. The pulse, the yield grows extremely rapidly, and there's a long tail due to the fact that even after the laser pulse is done, there are still a number of electrons that are above the photoemission threshold. So this decays, and it's not, you would notice that we're not doing crazy things to the pulse. The pulse has gone from maybe 50 femtoseconds to maybe 100 femtoseconds if you were to do a full with half max or something like that. But the nature and the density of the pulse has changed quite a bit. The photocathode physics will dramatically change the way space charge evolves the pulse later down the line. So I mentioned that we can calculate the quantum efficiencies. We can do so and compare them to data. The red line is my calculations of the quantum efficiency from the Boltzmann equation, and the blue line is data. So the agreement is quite good. These two curves here are for low fluence, and if you turn the fluence up, you get exactly what you would expect. You get an enhancement of the quantum efficiency only where the photon energy is close to the work function. Okay, recap. When photoemitting at threshold, the drive laser contribution shouldn't be ignored. The QE and MTE are dynamic parameters. Future cryogenic guns, they're cryogenic guns in DC, we're building some here, normal conducting RF guns being built at UCLA, and SRF guns being built at SLAC, which will need to pay particular attention to this fact. There is a rich unexplored physics here, just as some of the questions we're pointing to. What are the details of coherent multi-photon photoemission? What are the details of cryogenic electron-photon coupling in materials that we've never studied before? How do you calculate this in semiconductor photocathodes? All of these are open questions which we're actively exploring. And I think is a lot of great fun. So I'll pause here. We don't have a ton of time left. So I wanted to make sure that we get any questions out before I go on to the next subject. Yeah, Richard.
When you first introduced the dependence of quantum efficiency on temperature,
Yes.
I didn't understand what your explanation.
Okay. Is there something in particular that wasn't clear?
Everything.
Okay. So the quantum efficiency depends on temperature because the number of electrons that are above the Fermi energy is highly dependent on temperature. So if you're photoemitting such that only the electrons that are above the Fermi energy get out, the number of available electrons there is highly sensitive to the temperature. So if you're digging down deep into the crystal to get electrons out, if you're digging down deep into the crystal, the temperature, the smearing of this distribution doesn't really matter. The number of electrons down here doesn't really change. If you're only grabbing electrons here, the temperature will change the number of electrons available for emission dramatically.
Really discouraging.
What's that?
You would think that going to low temperature would be wonderful, and it's not.
It may not be. What is the case for other semiconductor photocathodes? What if we're able to explore, this is a great question, is this discouraging? So the question is this discouraging? I would say not necessarily. What is the case in other semiconductors? We don't know. What if we were able to exploit the rich band structure of the materials? Say we were able to photoemit from a momentum band that is inverted, a light hole band. In that case, the further you increase the temperature, the MTE might actually go down. So I haven't formalized these arguments, but I think there is a lot of room to explore this concept in light of photoemission from pristine surfaces where you can capture band structure effects.
You can't increase the electron density at the Fermi level, I wouldn't think.
At the Fermi level, no. The electron density is constant there, yes. But above it and below it, the density is changing, yes. Good questions. Excellent questions. Okay, let me do one last topic, and then I will take final questions. All my animations. Okay. So I want to talk about photoemission at small spatial scales. Photocathode electric fields can be very high. In some pulsed accelerators, they can be 100 megavolts per meter. That's a high number for those of you who don't have a scale for those numbers. Compared to other photoemission applications like XFELs and ERLs, diffraction, ultrafast electron diffraction, requires a pretty small number of electrons. The number of electrons is just given by how many you need to make a good image with them. 10 to the 6 is often a good number. Say you want 10 to the 5 electrons. If you do the calculation of how much charge density that can support, of how much charge density 100 megavolts per meter can support, that's a beam initial radius of 4 microns. And if you're using visible light, that's approximately 10 times the wavelength of light. So hearkening to physical scales, that's a pretty small number. And for the beam physicists in the audience, if the MTE is what you would get at room temperature, T equals 300 Kelvin, 26 millielectron volts, the normalized emittance is 0.8 nanometers, 0.8 nanometer radians. And for those of you who aren't accelerator physicists, note that most of accelerator diagnostics were built under the assumption that the beam emittance was about 1,000 times larger. So this is a new parameter regime for us when we're building hardware. We have to think very carefully about how to build hardware for tiny beams. So one of the experiments that we did at UCLA, which I was very proud of, was we made small beams. We made them short. This was the same picture of before, but we also made them very small. We used a lens to focus as tightly as we could down to the photocathode. And using a lens, the minimum spot size of the lens is directly proportional to the distance between the lens and the target. You essentially want to get the lens as close to the target as you can, and you're limited by the physical structure of the gun. You can't put the lens inside vacuum, or not easily, that is. So we got to about 8 by 18 micron photocathode spot size. But the downstream beam can be even smaller than the initial beam size. Typical screen diagnostics that we use in the beamline use fluorescent screens. We take the electron kinetic energy, we dump the electron kinetic energy into a crystal, the crystal generates light, and we image the photon distribution with a camera. What we did in this case, to try to get a handle on extremely small beams, is we put a microscope projected in vacuum to look at the photon distribution coming off of the mirror, coming off of the YAG. So incoming beam gets dumped into this fluorescent crystal YAG, cerium doped YAG, and gives photons that are magnified by the in-vacuum microscope objective. And we could see beams that were about 5 microns. In some cases, I saw a beam about 3 microns big, which for electron microscopists in the group may think that's huge. But for us, as accelerator physicists, that's tiny.
I'm not getting it. So wait, how do the electrons then come out? They fly through the mirror?
Oh, they fly totally through the mirror. Yeah, we don't see them. This was a 7 MeV electron beam. They go through the YAG through the mirror. Yeah, right. It's a good question. For lower energy systems, the YAG should be slightly conducting so they can absorb the electrons. We actually plan to make a diagnostic such as this in the Newman lab. So this concept absolutely works. It actually doesn't scale down well, though, because we're still imaging photons, and photons have a diffraction limit. Shorter and shorter wavelength scintillators would need to be needed to image smaller and smaller beams. That's not a great way to go. An alternate beam size measurement is a relatively simple one. Here's a very simple cartoon of what it is. You take a beam, you have a slit aperture of some size, and you scan the slit, and you measure the current that gets through. We actually have an interesting way that we plan to do small beam detection here at here in Newman Lab that not only gives us the spatial distribution, but the full phase space distribution. That is, if we were to use two slits which are sufficiently small, and you move them relative to each other, you can map out the position and momentum and how many electrons we're getting through at each spot. We actually have a macroscopic version of this, where each slit is like 100 microns, and that's what I used actually to make this picture. I used the macro MicroEMS measurement system. So the concept clearly works, but we need to do it at much smaller scales now in order to do ultrafast electron diffraction. And so I've been trying to cook up a system that can do this on a much smaller scale. I call it the MicroEMS for lack of better nomenclature. We're trying to design this so that we can get emittances less than 1 nanometer radian. So that number might not mean a lot to you, but it could mean something if I remind you that the CBB theme, one of the milestones of CBB theme 1 is to measure such a small emittance from a beam with 10 to the 5 electrons. So at 200 kilovolts design energy, I see a lot of people are looking at this. They have no idea what the picture is. So let me explain what the picture is. The picture is 2 slit systems, but you can't really see the slits because they're tiny. I'm thinking about slits that are 1 micron vertical slits made of silicon, which are lithographically defined. Then what you really see here is the fact that these things are sitting on top of 5-axis motion stages with DC servo motors, and you can get nice motors that have 200 nanometer repeatable motion steps. So if you do the math for how much emittance you can measure, the resolution should be well under a nanometer. And if you're asking yourself, can we actually make differential changes in the motion that small? Indeed, we did this at UCLA for dielectric laser acceleration, actually with a much more extreme aperture, a 400 nanometer by 1 millimeter long aperture. So applying that technology here is a pretty straightforward way to diagnose these tiny beams. I'm running a little low on time, so I was just going to mention that another project that we have going on is to change the way we think about the shape of photocathodes. Photocathodes have typically been planar surfaces from which we photoemit. However, if we take a hint from microscopists, the brightest sources of electrons that are used in conventional microscopy are very sharp tips, field-emitting sharp tips. They're not. They can be laser triggered, but are often just field-emitting. They have extreme electric fields, gigavolt per meter electric fields, and single nanometer effective source sizes. So these are extremely bright, extremely coherent electron sources. So it's a good inspiration. But in our case, we want a lot more electrons in a smaller temporal volume, so we can't use a single nanometer scale electron emitter. We have to use something a little bigger. But using this idea, we're thinking about using a microtip, not a nanotip, but a microtip. A microtip that has essentially 100 megavolt per meter fields at the tip with a base field of 10 megavolts per meter. 10 megavolts per meter is easily achievable in DC guns. 100 megavolts per meter would be a great achievement for DC guns. And with limited time, I'm not going to go into these details, but we're working on ways to simulate the photo emission from a curved surface in this very high field geometry, which requires a lot of computational tricks. Long story short, the image charges induced by a beam on a curved surface are an interesting problem to calculate, and we have a number of computational tools to do that. So, here are my conclusions. Brighter beams and ultrafast linacs are going to force a more complete merger of photocathode physics and space charge beam transport. I've given a few examples of this. New momentum distributions are going to mean new beam transport, maybe new ways that we simulate, but also new ways that we think about brightness conservation itself. Intense lasers, which are given by the application, are going to modify the photocathodes on short timescales. The search for higher fields may even change the shape of the cathodes themselves, as I just showed briefly in the last couple slides, and which we're calling microtips. But across the board, I hope that I've convinced you that we're going to need new start-to-end simulation modalities, where we start in the material and end in the beam dump and went through the sample the whole time. Simulation modalities are going to be required, and we're on our way. These are things that we're actively working on in CBB themes 1 and 3 together. So a bunch is owed to CBB as an organization and to the individual collaborators. Thank you very much to the photocathode group for giving me all the information to talk about, both here at Cornell and at UCLA. And with that, I want to thank you for your attention and your excellent questions. All right.
I'd like to make sure that we can receive questions from the remote participants.
So we were saying that we would like to get questions from remote participants if they can still hear us.
Gerard?
Yeah. I don't know.
Can you hear?
Because I...
Can you hear me? Hello?
You see who's logged in?
Yeah, someone is... Oh, let's see. Okay. So, what?
Hello?
Are there any questions from remote participants?
Yes, can you hear me?
You just asked for two of them individually.
Well, actually, one of them is us. Okay, so there are a few there. It seems that there are no questions. Are there any questions remaining in this room? Yeah, go ahead, Georg.
What's the current limit for one tip?
For one tip cathodes.
1.2.
What is the current limit? Oh, okay. I would say it's not useful for high spatiotemporal density. Currents can be 40 microamps, 100 microamps from those things. However, that's a DC current. It's not a bunched beam. For bunched beams, I have anecdotal conversations with the practitioners have said that a few electrons in a pulse is enough to destroy the coherence. The question is how you trade off coherence with the number of electrons in a pulse, but the number is single to few electrons per pulse.
Coherence in what sense?
Coherence in emins. Same thing. Any questions?
Hello?
Okay.
Makes the emittance grow when you have more electrons? It's space charge?
Yes, directly Coulomb repulsion.
So it's not,
that's right.
You can't extract more electrons.
You certainly can. Yes, you certainly can. It's just that
We had another limit for the number of electrons when the accelerating field was
yes,
something or the other.
that's right.
And
They would be very far from that limit because
but if you understood the space charge mechanism, you might be able to get around.
Well, you won't be able to get back past the space charge emission limit. Once the field is canceled on the cathode, no more charge will escape. However, there are gigavolt per meter fields, which are extremely high.
Yes,
and so,
they are
right.
1,000 times more.
Bear in mind the emitting surface is a nanometer on the side.
Take the nanometer emitting
Charles, can you hear me?
Yeah, then you can calculate it.
fundamental limit of how many electrons you get.
Hey, there's a question. Hello?
Oh, wow.
Excellent. That's very exciting. There was a question back there.
Well, I was going to say, you talked earlier about like maybe in the future we'll be able to emit electrons in some spatially organized lattice.
Yes.
Can I picture that like a lattice
Hello?
of these nanometer tips?
Yes, that's absolutely been a suggestion in the community, is to try to construct a tip array, a dense tip array to produce spatially organized electrons. Yeah, excellent question. Plasmonic structures as well have been suggested. Instead of tips, you can use locally confined electric fields from the light itself to make emission favored from one area over another. Yeah. That was actually how the whole business started. Is people wondered, would plasmonic cathodes make better beams because the beams were organized? And that begs the question: what is the scale of the disorder-induced heating? Thus, we answered it. Any other questions?
We had some problem hearing the audio from the remote participants, I think. Yeah, because George was trying to
Okay.
communicate.
Maybe someone can type the question.
You want to ask them to type this?
I think also if you mute if you mute your own audio, because the problem before was that it was like feedback. I don't know. If you mute, like, everyone,
But I want to mute only my microphone, actually. Not
if it's coming from Jared's lab. Oh, yeah.
That's it.
Or just unmuted.
I mean, if you mute Jared and unmute one other person.
Yeah, it could go on. Maybe George will maybe type the question.
Can anyone help me with that? I'm not clear what's being asked.
The point ends in matter.
Around the energy.
Yes. Okay, so getting a question from George that seems to indicate some confusion about when I said the temperature blurring of the electronic distribution at the Fermi energy not mattering. That blurring does not matter in the case that the electrons that you are emitting are primarily from much, much lower than the Fermi energy. In that case, the preponderance of the electrons have no sensitivity to the temperature, at least at the temperature scales that we're talking about. Of course, you could make the temperature larger, and it would make electrons further and further away from the Fermi energy more susceptible to temperature changes. But for instance, at 3,000 Kelvin, 1 eV of excess energy is barely sensitive to changes from 0 to 3,000 Kelvin. I hope that was partially helpful. Okay, if we have any other questions, we can certainly see your text, the text that you are, the text chats that you're sending.
You can maybe unmute all, so it's button. Okay. Let's try.
Are there any other questions from remote participants? You have been unmuted, so you can hopefully be heard. Young King, could you say more about end-to-end simulation? Absolutely, we've added to. So, end-to-end simulation would look something like a code that calculates dynamically what the electronic distribution looks like coming off of the cathode and simultaneously calculates the electric fields in the vacuum that those electrons that are being emitted experience. This may be important. A topic that I did not discuss is the key effect on the photocathode. If the quantum efficiency is changing as a function of the laser fluence, the amount of charge that's getting out changes, the electric field changes on the cathode, and that changes the work function. The field on the cathode changes the work function. So these three things are coupled. The laser is coupled, the charge density, and the work function are all intimately coupled. And they cannot be, in the case of laser heating, they cannot be decoupled from each other. You can't run one simulation to calculate one thing independently of another. In your particle tracking codes, you not only have relativity and space charge built in, but you have to the material in the photoemission process. So, excellent question. Thank you for asking it. Yeah. Text chats is the best solution for participants to ask questions. Are there any more questions on chat? Okay, apparently the audio has been in and out a lot. Any other questions? Okay, I guess, shall we adjourn?
Yes. Okay.
Okay, well, thank you, everyone. Sorry for the technical difficulties.
I would like to remind that the next CVB seminar is on November 1st. I think it will be at Lauren Berkeley Laboratory. It will be Daniele Filippetto talking about ultrafast electron diffraction.
Did you like?
It's distracting for me as well.
You think so?
Yeah.
Yeah.
A quick thing not to